Good evening and welcome to the DIE seminar of today. The speaker today is Matteo Tanzi, which is from Courant Institute of Mathematical Sciences in New York. So it's a pleasure to have Matteo here with us, and he will talk about random-like properties of chaotic forcing. So Matteo, the stage is yours.
Thanks a lot, Claudio. Thanks a lot for the invitation. It's a pleasure to speak at the DIE seminar. So let me start by saying this is a joint work with Paolo Giulietti and Stefano Marmi in Pisa. Yeah, as the title says, I'm going to talk about random-like properties of chaotic forcing. And so let me start by saying what I mean by forcing, what I mean by force system, and what I mean also by random-like properties. So when we have a dynamical system, and let's say we have a discrete time dynamical system, what we study usually, it's a map from a phase space chi, which is a set with some topological or measure theoretical structure. And what we study is we start from a point x in the space chi, and we apply the map f successively. So we start from x, we have f of x, then we have two iterates of the map f, and then three iterates, and so on and so forth. This is the usual discrete dynamics. What do I mean by force dynamics? I mean that instead of applying at each step the same map f, I'm now applying different maps. So I start from x at time 0. The first iterate, I apply f omega 0, and then I apply f omega 1 at the second iterate, and then f omega 2, and so on and so forth. And the f omegas, they are all functions on all maps on the phase space chi, and they're possibly different. And they depend on this parameter omega, which lives in this set capital omega. So we should think of these functions, f omegas, as maybe could be perturbations of a given function f. They could be just some functions. They might be unrelated to each other. The important thing is that we're applying different ones at each time step. And now I want to make a distinction between two kinds of force systems. The first one I call random forcing, where the sequence omega 0, omega 1, omega 2 of parameters are sampled identically and independently distributed with respect to some distributions. So at each time step, I draw one of these functions at random and I apply. I want to put this in contrast with deterministic forcing, where instead the parameters omega I that determine the functions f omega I, they are instead selected according to a deterministic process, where omega I plus 1 equals the application of a given map G on omega I. So I like to make this distinction, but this distinction is actually not stark. So randomly forced systems can be represented as deterministic force systems, and vice versa, some deterministically forced systems are actually random systems. So the distinction is not stark, but like in principle, like philosophically, we have a distinction with selecting maps randomly independently and selecting maps according to a deterministic process. So this is what we should have in mind. And basically, the result I'm going to talk about in a few minutes, it's going to compare random with deterministic forcing. But before giving the result, let me tell you what it's known. Like I'm going to just give a very, very short glimpse into what one can do when dealing with random forcing and what one can do when dealing with deterministic forcing. Also, yeah, I didn't say it, but like, please feel free like to interrupt anytime. Like if you have questions, don't worry. Please ask any questions you might have. So random forcing. When we're dealing with random forcing, a randomly forced discrete dynamical systems produces in a very straightforward way a Markov chain, a stationary Markov chain, xn, on the phase space chi. So xn is a sequence of random variables which are loosely defined in this way. So if I have xn, I can obtain xn plus 1 by applying f omega n to xn. And the fact that omega n here is a random variable makes this sequence a sequence of random variables and a Markov process in particular. And we can write down what is the transition probability for the stationary Markov process. So omega n is our sequence of parameters. I'm assuming that they're all identically distributed, and they're distributed with respect to the measure nu on the parameter space omega. And so if we have x, a point in the phase space, and a measurable set, we can wonder what is the probability that starting at x at time n, I end up in the set A at times n plus 1. The probability of this event, this conditioned event, it's the transition probability from x to A, which in this case can be expressed as the measure of the omega n such that f omega n of x belongs to A. So I'm sitting at x at time n. I'm going to apply one of these maps at random. What is the probability that I pick a map that lands me inside A? This is the transition probability of the Markov chain, which kind of gives us how the system evolves in terms of random orbits. What is the evolution of the system in terms of measures? If we have a probability measure mu on the phase space chi, the evolution of this probability measure is going to be given by this operator, which is the generator for the Markov chain, and it's defined as the integral of all the transition probabilities with respect to the starting measure mu. So if at time n, I'm observing my system in an ensemble of measure mu, to know what this measure will look like at times n plus 1, I have to apply the operator p. Doing some gymnastics with the double integrals and the definition of the transition probability given up here, we find that this operator, it's just the average of all of the transfer operators of the maps f omega that I'm applying with respect to the measure nu in parameter space. So we can think of this p as an average transfer operator. The average is among all the transfer operators associated to the maps f omega. A classical example to have in mind when thinking about these things is the case where phase space and parameter space say they're both R, or like an Euclidean space with some additive structure. And the maps f omega are given by application of a map f, a given fixed map f, plus omega, so plus some noise. So now this is kind of the setup. What can we say about this setup? There are different, so the theory of these Markov chains is classical, and there are different directions one could go towards. The one I'm interested in is the study of geometric ergodicity of these Markov chains. So if we define the k-step transition probability as a probability of starting from x at times n and landing in A after k steps now, not just one step, but after k steps, and if we denote by dTV the total variation distance between probability measures, then we say that the stationary Markov chain is geometrically ergodic if there are a constant c positive and lambda between 0 and 1 such that the nth transition probabilities starting in x1 and x2 become exponentially close in the total variation distance no matter the x1 and x2 I'm starting from. So ergodicity here is a term that's used like in the Markov chain literature. It's used in a slightly different way than in the dynamical system literature. But so what it means basically, so the consequence of this definition, the most important one is that under some assumptions on the phase space chi, one can deduce existence of a probability measure at a 0, which is a fixed point for the operator p. So if I start my system in an ensemble of measure at a 0 and I apply the operator p that evolves the measures, I'm sticking at a 0. I'm not moving from at a 0. And so for this reason, the reason at a 0 is also called a stationary measure. And if I start the system at a probability measure mu, any probability measure, and I apply the generator of the Markov chain to this probability measure n times, I'm getting closer and closer to the stationary measure at an exponential speed with respect to the total variation distance. So the picture for a randomly forced system, which is giving rise to a geometrically ergodic Markov chain, from the statistical perspective, which is the perspective I'm interested in this work and in this talk, it's kind of well understood. So there is exponential decay of stuff, like exponential decay of correlations, distances between evolution of measures and the stationary measure, it's exponentially fast, and so on. Now the question is, how do we decide whether the Markov chain generated by a randomly forced system is geometrically ergodic or not? There are criteria. It's a classical literature on Markov chains, on geometric ergodicity of Markov chain, that tells us that, for example, I'm giving an example of a result that proves geometric ergodicity, which is if we have a stationary Markov chain and we assume that there is a probability measure m such that there exists an epsilon and a number n0 such that the transition probabilities at time n0, they are all larger or equal than epsilon times this probability measure. So in other words, no matter the x you're starting from, if you wait n0 steps, all the transition probabilities starting from any x will all share a kind of common measure. That from that time on, that common measure evolves the same for everybody because just it's a common measure. And then you can wait another n0 steps and you will have, again, another fraction of the measure that's common and it starts evolving altogether. And this is what we basically give by a coupling argument gives the geometrical ergodicity of the Markov chain. But so this is the statement. The intuition behind it, or say the rationale behind this is that if there is diffusion in the system, so measures under evolution start to overlap after a bounded number of time steps, then the Markov chain will be geometrically ergodic. This is a kind of a simple statement that, of course, can be refined very much. And so I'm just referring here to classical references, and one can make these more refined by introducing petit sets or Lyapunov functions as kind of an Aries theorem. But I don't want to focus on this. This is not relevant for the talk. So the message of this slide is that there are ways to decide whether a Markov chain is geometrically ergodic or not. And as I mentioned before, once we decided whether Markov chain is geometrically, if that Markov chain is geometrically ergodic, then we kind of know a lot about the statistical properties of the system in terms of decay of correlations and so on and so forth. So this is the random setup. So under enough diffusion, we have geometric ergodicity of the Markov chain, we have exponential decay of correlation and spectral gaps in some sense. Now let me go to deterministic forcing. Now we don't compose maps sampled independently, but the way the maps are sampled is with respect to the deterministic process G. So a system undergoing deterministic forcing, it's better described with a skew product system, which is a map F from space of parameters cross the phase space. And the map F has the following form. The coordinate omega in parameter space evolves according to the coordinate omega only. So it's an autonomous evolution. The fiber, though, by fiber I mean the second coordinate, the chi coordinate, evolves in a way that depends also on the omega coordinate. And here, this dependence is given by a map, F, and it's understood that F omega x is what before I denoted as F lower script omega x. So dynamical systems with this particular form are called skew product systems, and there is a vocabulary in skew product systems that I'm going to use throughout the talk. So anything that happens in the first coordinate is usually referred to as the base of the skew product or the horizontal coordinate sometimes as well. Whereas what happens on the second coordinate, so the chi coordinate, is usually referred to as fiber dynamics or vertical coordinate. Let me show you why the skew product it's good to represent deterministic forcing is because when you take n and iterate the nth iterate of the map F, you find g n omega in the base. So it's just the n iterate of the map G. While on the fiber, on the vertical coordinate, you find applications of the maps F omega, Fg omega, Fg2 omega, up to Fgn minus 1 omega. So the skew product formalism very well describes deterministic forcing. And also let me tell you that I'm using this the word in deterministic forcing, but actually in the dynamical system literature, this is usually known as a random dynamical system, right? When one has like farther properties of G maybe, but this is what we think about in dynamics when we think about the random dynamical system. So also about the skew products, like literature is vast. The literature is vast. I'm just going to give a glimpse of things I care about to the end of this talk. And I'm going to state very loosely a meta theorem of results concerning this kind of systems. The meta theorem goes along the following line. So one usually assumes some properties for the map G. Usually this property, they're not very demanding. Usually G omega should have a measurable structure, an invariant measure, and maybe this measure is ergodic. And maybe the function G is invertible sometimes. But so G is a deterministic process, and basically the main assumption is that it's an ergodic process. The maps F omega, the maps that I'm composing, they're usually assumed to share some good properties. And these good properties are usually good properties of the transfer operators of these maps that when acting on some functional spaces, they have a good spectral picture. And these maps F omega could have like a uniformly good spectral picture. So all of them have, say, a spectral gap, and the spectral gap is uniform size across the maps F omega. Or these properties, these good spectral properties could be sometimes good spectral properties on average. So not all of the maps F omega have these nice spectral properties, but on average they do. Under this assumption, the conclusion of the meta theorem is your favorite statistical property, like existence of a stationary measure, exponential decay of correlation, CLT, and so on and so forth. Examples of this meta theorem, and here I'm simplifying very much. Like it's more complicated than this, but just like to give an idea of what one can usually say in this scenario. And some examples are, one could assume that F omega are all uniformly expanding maps. So there is a geometric structure on chi, and F omegas are maps that are expanding distances on the phase space. Or F omega could satisfy some Lazotta-York inequality, so the setting could be a little bit more abstract. And so, for example, F omega could be piecewise expanding maps. Or F omega could be like a hyperbolic diffeomorphism or non-uniform hyperbolic maps. And here I'm giving like some partial list of people working on this, but like the list could go on like much longer. So apologies to anybody I could have left out. So this is the general result one could have for deterministic forcing. So I want just to summarize and make a comparison between what we can expect for random forcing, what we can expect for deterministic forcing, and more precisely, actually, what I'm interested in now, it's the assumptions, right? So for random forcing, we have very strong assumptions on the sequence omega n. The sequence omega n has to be an independently identically distributed sequence. So it's very strong assumption. Whereas in the deterministic forcing case, the assumptions on the process omega n are much weaker. So usually, as I said, G is only assumed to be ergodic. For what concerns the fiber dynamics and the dependence of the fiber maps on the parameter omega, we have mild assumptions on the random IID forcing. Namely, we need that the dependence of F from omega is such that we have diffusion in the system that ensures geometric ergodicity. While for the deterministic forcing, there is almost no assumptions on the dependence of F from omega, maybe just some measurability assumptions, some very, very weak regularity assumption. For what concerns the actual maps F omega and their dependence on the phase state variable, there is weak or no assumptions in the random IID forcing. All of the assumptions are in these other two ingredients, while for deterministic forcing, we usually have very strong assumptions on F omega. So the F omega, as I said in the previous slide, they should kind of share some common good property, like hyperbolicity or something else, but they should share some good properties. And this kind of restricts a lot the choice for the maps F omega. What I'm going to talk about in this talk, it's deterministic forcing. So I'm on this column here. But the assumptions, they actually resemble more this other column here. So I'm going to give very strong assumptions on G. Namely, G is going to be a uniformly expanding map, and the uniform expansion is actually going to be very large. So we should always think of G as being like a 10-100 omega mod 1 map. And I'm going to put mild assumption on dependence of F omega from omega, still to ensure some diffusion going from the base of the skew product to the fiber. And I will put weak or no assumptions on the map F omega. So there is not going to be a spectral picture, a good spectral picture in this situation. These are the assumptions. What about the results? The results, they're going to be in the direction of what we have in the random forcing with a caveat, which is going to be evident in a moment. But so the idea is to describe the statistical properties of this system in terms of existence of a stationary measure, convergence to the stationary measures, speed of convergence to the measure, and consequences like decay of correlations. So the setup is the following. Just to fix ideas, let's consider omega to be M1 dimensional torus and chi an M2 dimensional torus. G, as I anticipated, it's a uniformly expanding map, C2, and with bounded distortion. Uniformly expanding means that when applying the map G, the action of the differential on tangent space stretches the norms of the vectors by a fixed factor, not fixed actually, so the factor could vary, but the factor is lower bounded by this sigma, this parameter sigma, which is the minimal expansion of this uniformly expanding system. And the system has bounded distortion in this sense. So there is this parameter capital D that measures the distortion of the system. And so with D equal to 0, we don't have distortion. And actually here, sorry, this is a typo. So D could actually be equal to 0. With D equal to 0, we have no distortion. With D larger than 0, we have distortion, and the larger D, the larger the distortion. And so these are the assumptions on the map G. Then we have assumptions on the map F, which for now are very, very weak. It's just like a Lipschitz regularity assumption. And Lipschitz, it's not so important. We believe that we can change the proofs to allow for older, for example. But some very weak regularity of F, it's needed here. then what we do, we study the skew product, which is obtained by putting G in the base of the skew product and F omega X in the fiber. An immediate consequence of these assumptions, it's that from what I imposed on G, G has a unique absolutely continuous invariant probability measure, which I will be denoting by nu G. And this measure has a density, which I'm denoting by rho G. And this is a density with respect to the Lebesgue measure actually on TM1. Sorry, it's another type. So this is well known. These are well-known facts for uniformly expanding maps with bounded distortion. So the existence of these unique invariant measures. These are, say, the minimal working assumptions. Now let me give you the main assumptions of the results I'm going to prove. I'm going to present. And to do so, I have to introduce what we call the random counterpart of the deterministic forcing, which is the following. For all of the maps F omega, we can define the transfer operator for the map F omega. And we can define an operator going from the measure on TM2 to the measures on TM2, which is just the average of all the transfer operators with respect to the measure invariant under G, the unique invariant probability measure for G. And this operator, of course, generates a stationary Markov chain that has transition probability that can be written in this way. So here we are starting from a measure nu G and maps F omega, and we are producing a Markov chain out of it. And we call this Markov chain the random counterpart of deterministic forcing. And it's just like a name, but it means like a very simple thing, which is I'm considering like the random system, the randomly forced system, where I apply maps F omega 0, F omega 1, F omega 2, where omega 0, omega 1, etc., they are sampled independently according to the measure nu G, which is the invariant measure for the base map G. So we have this deterministic forcing. From it, we can construct a random counterpart. The main assumption is that this random counterpart is geometrically ergodic. And I write this by assuming that there is this C and this lambda, such that if I start from true probability measure mu and nu, and I evolve these true probability measures according to the random counterpart, then this is less or equal than C lambda to the n.
Excuse me, Matteo, can you just recall us what is rho G in the definition of EXA?
Yes, rho G is the density for the measure nu G.
Ah, okay.
So I could have written this actually just d nu G of omega. Yeah.
Okay, thank you.
So this is the main assumption. Let's see what the result states. We are assuming that F it's a skew product as in the setup, satisfying hypothesis 0.1 to 0.3, and satisfying the main assumption. So this is the statement. So let me just maybe before actually reading the statement, some notation. dW here, it's the Wasserstein distance between probability measures, which is a weak way of measuring distances between probability measure. It's a weaker distance than the total variation distance that appears here in the main assumption. So this is the Wasserstein distance, and another notation I have to explain is this pi in front of this measure. Pi, it's the projection of measure to the vertical marginal. So pi acts on measures which are on TM1 cross TM2 and gives a measure on TM2. And it's, so the vertical marginal means you have a measure on this full space, you just squash the measure all on to one coordinate, the vertical one. And this is the definition of the vertical margin. MH here, it's a set of measures on TM1 cross TM2, it's kind of a regularity class, which I'm not going to talk about now. It's going to come up in the proofs. So we cannot give the statement for any initial measure mu, but this measure has to be like inside some regularity class. So now that we have the notation out of the way, let's read the statement. There is a eta bar, a probability measure, and constants lambda tilde in 0, 1 and c tilde positive that satisfy the following. Fixed any precision epsilon, there exists sigma 0 such that if sigma is strictly larger than sigma 0, so if the expansion in the base is larger than this given expansion sigma 0, then the evolution of the vertical marginals of measures under the push forward of f gets closer and closer to eta bar exponentially fast modulo the precision epsilon. So modulo this error epsilon, we observe convergence of the vertical marginals to this probability measure eta. Okay, so now I'm going to comment on this statement. And the first thing I'm going to comment is the main assumption. Okay, so we have this main assumption. We know that there are results to check it, but results in the theory of Markov chain that allow us to check if a certain operator exhibits geometric ergodicity. But what does this, how can we find like sufficient conditions given our deterministically forced system, given our skew product? Are there sufficient conditions that ensure that the main assumption is satisfied for the random counterpart of the deterministic system? The answer is yes. And first of all, let me remark that P depends only on F, so it depends only on the fiber maps and on the invariant measure of G. It doesn't depend on the particular choice of G. If two maps in the base G have the same invariant measure, the same absolutely continuous invariant probability measure, then P, the random counterpart, is going to be the same for these two deterministically forced systems. Then what is a sufficient assumption for the main assumption to work is that the choice of F, so the way F chooses the maps according to omega, if this is sufficiently smooth, say C2 in the omega coordinate, and the dependence of F on omega is non-degenerate, then this is going to imply the main assumption. This is one example when M1 equals M2 equals the number M, and F omega X is given by application of a map Tx that could be anything, could be just a Lipschitz function of some kind, plus H omega, where now H is instead the C2 local diffusive. This is an example of where the main assumption holds. The sufficient assumption is by no means necessary, and let me stress that it does not imply, in general, a good spectral picture for F star. So there is lots of freedom here on how to choose this T, and so in general, there's not going to be a good spectral picture for F star. So this is like a comment on the main assumption. Let me comment on the meat of the result, which is like this sigma 0. So what the result is telling us loosely is that if we fix any precision epsilon, there is going to be a sufficiently large expansion in the base that will give this this exponential decay result with respect to the precision epsilon, modulo the precision epsilon. Sigma 0 here, given by the statement, depends on all of the datum of the problem. So it depends on the dimensions, M1 and 2. It depends on the distortion in the base, D. It depends on L, which was the Lipschitz constant of F. And depends on C and lambda, which were the parameters appearing in the main assumption. And of course, if I want this inequality to hold with a small epsilon, I'm going to have to pick a very large sigma 0. And so fix the datum, one might have to pick a very large expansion in the base to ensure that the precision of the result it's as good as we want. It's actually easy to produce examples of maps G0 with very large expansion. You just pick iterates of a given map G0. And this is going to give G with minimal expansion, the minimal expansion of G0 to the power n0. And all of these maps G, they all have uniformly bounded distortion in n0. So this produces examples of expanding maps with arbitrarily large expansion and fixed distortion. The next thing I want to remark on, it's of course like the elephant in the room, which is the approximate nature of the result. So this is not what we're usually used to, and maybe it's not what we like, but that's what we get in this case, I think. I don't think we can go better than this, just because even the existence of a physical measure or an SRB measure for F, it's not known or given. There is a dominated splitting in the system, just because in order to make this result meaningful, we need to have like a large expansion in the base. And a large expansion in the base is likely to produce positive Lyapunov exponent and a dominated splitting with an expanding direction, which is roughly aligned with the horizontal direction. The problem is that we don't have any information on what happens on the transverse directions to these expanding directions. And furthermore, there is low regularity in this transverse direction. So globally, F, it's only a Lipschitz function, or maybe we can probably push this to older. So there's very little chance for existing of a physical or SRB measure under this generality. And so this is why we end up with this approximate result, epsilon. So this is maybe a good time to pause, if there are any questions on the statement, on the theorem, or anything else.
Can I just ask a quick question? So do you have any information on eta bar, for example?
Yes. Oh, actually, yes. Maybe I think yeah. So there is a remark on eta bar. Thanks. Yes. So eta bar is an approximate stationary measure. So it plays the role that the stationary measure played when we were dealing with random forcing. Eta bar, in the case where G has no distortion, it's actually the stationary measure for the random counterpart of the system. However, when G has distortion, as non-zero distortion, this might not be the case. Eta bar can be a different measure. It has to do with another operator, which if I have time, I will talk about later when I go through the sketch of the proofs. But in general, this will be different. So the eta bar and the fixed point of P can be different. And eta bar is in general, of course, not invariant under the push forward and the marginal. And so this is why it's just an approximate stationary measure. Yeah, thank you. So, yeah.
Question. Hi. Do you have any estimate on sigma naught in terms of epsilon?
So we have an idea. We have rough estimates. I didn't prepare them on the slides. We have an idea of rough estimates, but this is actually going to come up at the end of the talk. We don't have good estimates. So the honest answer is that we don't have good estimates at the moment on the depends on sigma 0 and epsilon. Just to spoil a little bit the ending, it can depend a lot on the interplay between the expansion in the base and the fiber, the maps on the fiber. So this is just now a quick corollary. If we know this on the evolution of measures, this is going to tell us something about decay of correlations in the system. And we're still going to get an approximate decay of correlation result. It's kind of this statement here in the corollary is the dual statement of what's above. So there is some work to do to go from one to another, but it's not the meat of the work. Okay, so if I haven't forgot about any other slides after this, I would proceed with giving a sketch of the proof. Actually, how much time do I have left?
I think we can go for 15 minutes.
Okay, sounds good. Yeah, so I will first of all give a sketch of the proof in an easier case. The easier case is when the dimensionality of both parameter space and the fiber is 1. And the map G, has no distortion. So given the regularity assumptions on G and the fact that it has no distortion, this can only be sigma omega mod 1, where sigma, let's take it orientation preserving. And so it's a sigma, it's a number larger, strictly larger than 1. And then we have f omega x, which is our fiber maps. The main tool and the main ingredient of all of the proofs is the following class of regularities for measure on the product space T cross T. We say that mu has Lipschitz disintegration if it admits a disintegration mu omega with respect to the partition into vertical fibers. So this is a partition of T cross T into like the vertical fibers. And so mu will have a disintegration with respect to these vertical fibers, and not just one. And if we find a disintegration which is Lipschitz as a map from omega to mu omega, where omega is on the torus with the Euclidean metric, and mu omega is on the space of probability measures on T with the Wasserstein distance. If there is such a Lipschitz disintegration, we say that mu admits a Lipschitz disintegration, and we denote by lip mu the Lipschitz constant of mu. Here with the absolute value, I'm always denoting distances, Euclidean distances on tori of any dimension. And so this is the ratio between, I mean, it's the usual definition of Lipschitz constant. Why this class of measure is important is important because it's going to give an invariant class of measures. And maybe, yeah, I should comment that basically what this invariant class of measures is, it's a class of measures which are regular in the omega direction. And the fact that this class of measures is going to be invariant is not surprising, just because the dynamics is regularizing on the omega direction. So if mu now it's a measure on T cross T with horizontal marginal equal to the bag, and here the bag it's the invariant measure for G, so it's not this is not a coincidence. And if mu has a Lipschitz disintegration mu omega, then we can say that also f star mu will have Lipschitz disintegration, and this Lipschitz disintegration is given by this expression. Let me give this as a given, like this is one, if one plays a little bit with the push forward, that's what comes out of the expression for the disintegration of f star mu. So we have control on how the disintegration evolves, and so we can capitalize on these and find estimates on, starting from mu with Lipschitz disintegration, estimates on the Lipschitz constant for the disintegration of f star mu. And this is what we find. So the Lipschitz constant of f star mu is less or equal than L sigma minus 1 times the Lipschitz constant of mu plus L times sigma minus 1. L here is the Lipschitz constant of f. So it's the regularity of the fiber, if you want. From this inequality, we find our invariant class of measures, which are the measure which have Lebesgue horizontal marginal and Lipschitz constant and Lipschitz disintegration with Lipschitz constant less than or equal to L, where L it's a parameter, and to make this set gamma L invariant, L should be larger than capital L times sigma minus 1 divided by 1 minus L sigma minus 1. And by the way, in the statement of the theorem, where I was leaving the set where mu was defined, like this is the set where mu is defined. And it doesn't have to be like the horizontal margin doesn't have to be the bag. There are like some generalization we can make, but just like to make the presentation clear, let's think about this as having horizontal margin on the bag. So how do we proceed? So the statement of the theorem is a statement about being able to control the horizontal marginal horizontal marginal of measures under evolution, under push forward. So, sorry, not the horizontal, the vertical marginal. So this pi here is the vertical marginal that, given a measure mu, we can, and with this integration mu omega, we can express the vertical marginal of mu with this formula. So it's just going to be the average of mu omega with respect to the Lebesgue measure. And now if we pick mu, a measure in this invariant class, then we can write the following. The vertical marginal of f star mu, one can do some computations, and you find that this is what equals to. So it's just f omega star mu omega with respect to the integral with respect to the Lebesgue measure, again the variant measure for G. Then we can add and subtract the vertical marginal of mu from mu omega and rearrange the terms in this way and recognize that this first term, it's the application of P, the random counterpart of the system, to the vertical marginal of mu. Plus this term, and what about this term? So this term, since mu is in this regularity class, this term will have Wasserstein norm of this order. And when sigma becomes large, this number here goes to 0, which means that this norm goes to 0. The idea here is that when sigma is very large, this mu omega, this integration is almost constant in omega. And so it's going to be very close to the vertical marginal, which is just an average of the measures mu omega in this integration. So we have that vertical marginal of f star mu, it's P applied to the vertical marginal of mu plus an error. And so we can use this and take higher iterates and do some work to show that this is how vertical marginals evolve. So if we have two measures, mu1 and mu2, we evolve under the push forward and we take the vertical marginal. We can upper bound these as c lambda to the n plus epsilon. Where epsilon now, it's going to depend basically on this number, and to make epsilon small, we will have to make sigma large. And from this proposition, the theorem basically comes as a corollary of this proposition, with some work, of course. So this is the proof in the case where G has no distortion. Let me give just a glimpse of how we can modify the proof when there is distortion. Actually, the proof, it needs like an extra idea. We cannot straightforwardly, or at least we couldn't straightforwardly generalize this proof to the case with the distortion. The main reason is that now mu has horizontal marginal nu G. So before we had Lebesgue, but now the invariant measure for G could be some other measure. So this is going to be the horizontal marginal for G, for mu, and this integration mu omega. Then this is going to be the expression for the disintegration of f star mu. It's a bit more complicated expression, but in spirit, it's the same as in the case with without distortion. The main problem now comes when we use this expression to upper bound the Lipschitz constant of f star mu, of the disintegration of f star mu with respect to the Lipschitz constant of mu. And there is this extra term that we didn't have before, that depends on the distortion, and that becomes large when the distortion is large. This means that the invariant classes of measure, they are not made anymore of measures with almost constant disintegration when sigma becomes large. So we have this kappa d here that makes this class of measures, they are not constant, like the disintegration, they're not constant. So we cannot apply the same reasoning as before, because when sigma becomes large, this number doesn't go to 0. So what can we do? so some notation, G is a C2 local diffeo of T, so it has D invertible branches. D is the number of branches. I are the intervals on which these branches are defined. Instead of considering the projection to the vertical marginal, we consider something a little bit more complicated, where we start from a measure mu, and instead of projecting, squashing everything to one vertical marginal, we project these on a d-dimensional space where on d-dimensional vectors where the vectors have components which are measures. And to obtain these vectors, we just take the average of mu omega over the intervals II, so over the intervals of the Markov partition. This is a sort of a coarse graining of the disintegration of mu. The disintegration of mu omega, it's something that's it's like continuous. So for every omega, you get a mu omega. Here we are coarse graining this disintegration and lumping some of the mu omegas together. So all of the mu omegas that sit above one of these intervals, we are lumping it together, and we get this coarse grain. The advantage of this coarse graining is that when sigma tends to plus infinity, mu omega is almost constant on the intervals II, and it's roughly equal to these components, to the components of the vector. And we can recover the vertical marginal from this coarse graining by this expression. So we can keep track of the vertical marginal if we can keep track of this disintegration. And we can keep track of this integration by introducing an extra operator L, which goes from these vectors of measures to this vector of measures. And as the advantage that, so why this operator is useful? So this operator is useful because if we take the coarse graining of the disintegration and apply the operator, this is going to give something very close to taking the push forward of mu and then the coarse graining. And this is the first good thing about this operator. Second good thing is that it has good construction properties. So basically, if we go back to the proof of the case without distortion, now we have kind of the similar idea, but instead of P, we have the coarse graining delta. So instead of pi, we have the coarse graining delta, and instead of P, we have the operator L. And the eta bar, the approximate stationary measure eta bar, it's going to be a measure that has something to do with the fixed point of this operator L. And here I'm just going to put on the screen the definition of the operator. It doesn't look maybe very nice, but it's actually not so bad. Like it's just we should think of L as a matrix where each entry it's an operator, and the operator is kind of an average of the transfer operators of the function. So I have still 5 slides on the talk, but I think I should stop here. And maybe like if somebody has questions, I can go back to other things. But yeah, thank you. Thank you for your attention.
Hey, thanks, Matteo. So let me clap for everybody. Then let me ask if there are questions or remarks from the audience. Then, since maybe I can ask another quick question. So the first thing is that more a comment maybe than a question. So you always presented your results by saying that we are talking about approximate decay of correlations, for example, in the corollary. But I think we can also interpret this result as saying that it's kind of finite time. So this is, I mean,
Yes. So when you have an eye to application, so there are 2 things. So one thing is finite time. So you will never observe your system like for infinitely long time. So even like when you have exact decay of correlation, you will always maybe have an offset. And the second thing is like when you have an experiment, you always have measurement errors. So you will never be able to measure correlations exactly. So there will be always measurement error. And if the approximation term in the theorem is below this measurement error, exact and approximate decay of correlation, they're really undistinguishable. Yes.
Yes, thanks. So, and the second thing then probably is about something that you just skipped. So I was going to ask about examples.
Yes.
Yes.
Yeah, so one example I wanted to give is, so we can prove that the case with distortion equal to 0 and distortion different from 0, they actually give rise to different eta bar, even if the base maps G have the same invariant measure. So here I have two examples. So I'm numerically evaluating the vertical marginal. And here it's the vertical fiber maps. And here are the two different kinds of maps that I consider in the base. The first one is the usual distortionless case. It's in this case is a 10 omega mod 1, but it's going to be 100 omega mod 1 in the simulations. And here it's another map, which still keeps Lebesgue measure invariant. That's a unique absolutely continuous invariant measure. But now it has distortion. There are still like the same number of Markov intervals in the partition. Kind of like you still have like full, by this I mean like you have still full branches on intervals of size 1/10, but now each interval of size 1/10 is subdivided in a part where the expansion is not too large, like here is roughly 5 expansion, and then there is like a very small interval where the expansion is extremely high. So here the graph is almost vertical. This ensures that if you start on this interval, you're going to remain for a long time on this interval before you actually jump to the other one. So this means that the series that you observe when you iterate this map and you iterate this map, they're very different, because in this case you will jump all over the place. In this case, you will stay on this side for a long time and then jump on this side and stay on this side for a long time and then maybe jump back. So they're very different. And what happens when we simulate the vertical marginals, this is the vertical marginal you obtain when you put the random process instead of those two deterministic processes. So this is for reference. And this is the comparison of what happens when we have on the first column no distortion, and in the second column we have distortion different from 0. And so we see that when the expansion becomes large, in the case without distortion, we recovered like a vertical marginal very similar to the completely random case. In the case with distortion, we recover vertical marginal, which is actually very different. And the reason why it ends up to be different is that when we are on this interval, 1/1, we apply north-south diffeomorphism and a noisy north-south diffeomorphism, which is very close to the identity. So if we apply these two branches like interchangeably, and the interchange happens very often, the system doesn't realize that there is a north-south north-south diffeomorphism here. But if we apply actually this branch for many times in a row, then even if phi itself it's close to the identity, phi to the 100 or phi to the even phi to the 10, maybe it's not close to the identity anymore, and that's what causes this concentration. And here I'm showing simulations. These are numerical simulations, but actually this is something we prove rigorously. The example it's worked out analytically and shows that the two vertical marginals are going to be different.
Okay, thanks. So the questions.
So I have a question about this picture, the second one. So you show analytically that it converges to a delta measure?
No. So analytically, we can show, so what we show analytically is that the two measures are farther apart, say, the distance between the two measures, eta bar, in the two cases, it's larger than, I don't know, 1/4. And we show this by proving that in one case, eta bar, it's going to be like in the random case, so it's roughly equidistributed on 0, 1. While in the second case, like the measure of, say, this interval 0.4, 0.6 is larger than 1/2 or something like that.
But you don't know what happens in the limit?
No, like we cannot analytically compute the vertical marginal in this case. In this case, yes. So in this case, should be, I think it should be. Well, but even in this case, it's not clear analytically what it will be. It will be almost uniform, but not exactly uniform, just because there is this north-south diffeo that kind of makes things a little bit just slightly concentrated around 1/2, but just very, very slightly.
Okay, thank you.
Okay, are there questions? Seems also the chat is empty, so maybe it's time to thank Matteo again.